Okay, now we prove that the integral f along q j over n is equal to the integral of f along q j plus 1 over n. Okay, actually k, not j, k, it's level, it's different level, k to k plus 1. In the book, they didn't write the n over n, it's okay. Well, let's see. Remember here, we have this closed polygon. This is one polygon, and actually you have a lot of one. So this is one, and the other one, and finally, it's like you have a cube. You remove the faces, just have the skeleton, just have the sides. Okay, so this is a P 1K, P2K, P3K, and P4K. They're just 4 sides. Okay, so the polygon, you see that the top belongs to the upper level, the bottom belongs to the lower level. But what about the columns, the vertical side? What about the vertical side? Right? So let's see. This one, you have one integral, you have another integral, another integral, another integral. We want to show they equal to each other. And this equality, if I move this to the other side, you will see this is equivalent, this condition, it is equivalent to the sigma j from 0 to n minus 1 integral f pjk is equal to 0. It is equal to this. Why it is equal to this one? The thing is that, you see, this polygon, this is only talk about the top level, and this one, this one only talk about the top level, this one only talk about the bottom level. When we have k is a bottom, we'll have k plus 1 is the top. There's no column, but why we say you can get the equivalent condition about the whole top and the bottom. The thing is that, so for example, for this pj plus 1, for pjk, and this one is a pj plus 1k. Here and here, yes, this one. I move it to the other side, I get subtraction. I will change the direction. So the bottom is, assume the bottom is always from left to right, then the top will be from right to left. And then for pjk, you use this vertical side upward, this vertical side downward, the pjk. But for pj plus 1k, it uses this right side upward and this bottom side downward. So you check here, this one you have up and down. One's up, one down, so it cancelled. So it is cancelled in the integration. And here will be cancelled with the next pj plus 2k, and this one will be cancelled with a pj minus 1k. And you remember it's a loop. So all the vertical side, the integral along those vertical side will be cancelled because one is up, one is down. You check here, one is up, one is down. Here, this is one is up, this okay, you have to watch from inside to outside. Then this is down, this is up, and here is down, here is up, here is down. Okay, don't look at inside. If you are the person, you should stand inside, don't look up outside. You should stand inside of this cube and check the orientation. Stand inside the cube, check the orientation, then you will have the right one. Otherwise, you will get the wrong direction. Okay, so this equality will be equivalent to the sigma, will be equivalent to the integral along all the walls, the integral along all the walls. Okay, so let me write it. The author gave the very good sentences. So it says the integral of pjk the integral of a pjk includes the integral over, okay, vertical. This is a zjk, zj plus 1k, zj plus 1k plus 1, okay, over zj plus 1k and zj plus 1k plus 1 up, and the other one, it's from z. Let's just talk about this one. It includes this one, and integral f along p j plus 1k also includes the integral over what? Over the opposite direction. Zj plus 1k plus 1, zj plus 1k. They integrate opposite one, and hence they are cancelled. They have different direction, they are cancelled. Well, okay, so you just go through all possibilities, or you go through all the walls. You will cancel all the columns. You only leave the top and the bottom skeletons. Once we notice that this is equivalent to the sigma of the sum, we see what we have proved. We have mentioned the integral of f over each polygon is over each polygon is what? Already. We already showed the integral of f over each pj1k is equal to 0 for j between 0 and n minus 1. So we proved that f over q, j over n, k over n is equal to the integral f q k plus 1 over n. Okay, so this is a q n plus 1 over n. K over n, and you just build add additional columns to get the size, and this is a p1k, p2k, p3k, p4k, p5k, and p6k. And over each small wall, the integral is 0. So add them together is still 0. And also here it's cancelled. This is up, down, up, down, up, down, up, down. So up, down. Well, here up, down, you have to look inside, then this becomes a down on the left, up on the right. Check always inside, and this is a up, down. Okay, that is the strategy for this part. All right, so now we completely finish the proof of a 6.7, and the 6.7 implies 6.6. All right, okay. So the theorem 6.6 is a corollary of this proof of this theorem. Remember, the winding number is defined by the integral. So the corollary of this homotopic invariance is that if gamma is a closed rectifiable curve in G such that gamma is homotopic to 0, then the winding number of gamma with respect to W is always equal to 0 for all W in C minus G. Right? So you just check that the winding number is defined by this for A not belong to the trace of gamma, not belong to the trace of gamma. And you show that if gamma is trivial, constant gamma, over the constant 0, A is not, of course, that constant point should be inside the G. Constant point is inside G. So this winding number is 0, then by the invariance property, the integral along gamma should also be equal to 0. Just use the definition because this function will be analytic. Remember, it will be analytic because you should this W. Because you choose W outside of G. Okay, once W is outside of G, 1 over Z minus W is analytic. Analytic, then integral 0, everything is done. Okay, by the invariance property. Okay, excellent. So we do have this property, the homotopic trivial, homotopic to 0 imply the winding number equal to 0, but the proof depends on the homotopic invariance. You cannot go backward. Okay. Okay, so the condition from homotopic to 0 imply the condition, the winding number is 0, but the converse statement is not true. Well, it's your exercise. Check the exercise 8. Check the exercise 8, okay? So you do have the winding number equal to 0, but the it's not homotopic to 0. And another thing we can another application of this stuff is that we can use the winding number to see which some closed rectifiable curves are not homotopic. All right, so from this observation we can see that if gamma 0, gamma 1 are two closed rectifiable curves, in G, then if gamma 0 homotopic to gamma 1, then not use this then. Okay, not use this. If gamma 0, gamma 1 are two closed rectifiable curves in G, if gamma 0 is homotopic to gamma 1, then the winding number of gamma 0 with respect to A is equal to the winding number of gamma 1 with respect to A. They will share the same winding number. Okay, so on the other hand, if the winding number of gamma 0 with respect to A is not equal to the winding number of gamma 1 with respect to A, then they are not homotopic. They are not homotopic. You cannot deform one continuously to the other one. All right, so that's a equivalent statement. All right, the application will be like this. If we have gamma 0 equal to E 2 pi IT, counterclockwise orientation. Gamma 1 is E negative 2 pi IT. How can you convince people counterclockwise orientation cannot be continuously deformed to clockwise orientation? Cannot be continuously deformed to clockwise orientation. Cannot. It's because the winding number of gamma 0 with respect to 0 is 1. The winding number of gamma 1 with respect to 0 is negative 1. They are different. So these two curves do not have continuous deformation between them. Okay? All right. So we always talk about closed rectifiable curve. Closed rectifiable curve. It has to be closed because we want to define the integral, the closed integral, the Cauchy's integral formula. It's not Cauchy's theorem requires that. All right. Now let's see what if we don't require closeness, we just require rectifiable condition. With that condition, we can also define such homotopy stuff. So, okay, so if gamma 0, gamma 1 from 0, 1 to G are two rectifiable, not necessarily closed. Two rectifiable curves in G, such that, well, if they are not closed, then we need other condition. Gamma 0 of 0 is equal to gamma 1 of 0 is equal to A, and gamma 0 of 1 is equal to gamma 1 of 1 is equal to B. It's like this. This is gamma 0 of 0, gamma 1 of 0. This is point A. This is gamma 0 of 1, gamma 1 of 1. This is point B. They share the same ending point. They share the same ending point. Okay, then gamma 0 and gamma 1 are fixed endpoint. Fixed endpoint homotopic. They will write fixed endpoint homotopic. If there is a continuous map capital gamma from I squared to G such that, so basically we want to do this, so we deform this way and like you hold the rubber two ends of the rope and then you shake it. Okay, so first gamma S0 is little gamma 0s, gamma S1 is little gamma 1 of s. So you do have the upper bound and lower bound, and they must fix the point. Gamma 0 of t is equal to a, gamma 1 of t is equal to b, not 1, is equal to b for all st. Two conditions, those two conditions. If you go back and check the definition of a homotopy, you will see that here in the homotopy we don't require this is A, this is B, we just require this one is equal to this one, that's it. So that's why closed curve can be like this. General homotopy about closed curve, you may translate the fixed the endpoint, it's okay, it doesn't matter. Right? Okay, this is a fixed endpoint homotopy. Fixed endpoint homotopy. And this fixed endpoint homotopy is also an equivalence relation. This relation of fixed endpoint homotopy is also an equivalence relation. You can imagine that, or you can just sketch it if you get the other curve. Then just get, it looks like you have a lot of bananas together, right? So it's also equivalence relation. Now let's use this graph and see what I'm going to do. I have A and B, whatever direction. This is, yeah, this is A, this is B. We have gamma 0 and gamma 1. We assume gamma 0, gamma 1 are homotopic in G. Then gamma 0 minus gamma 1, like this direction, is closed. Is closed. Of course, gamma 0, gamma 1 are rectifiable. I'm not going to write that word. And then let's see, I'm going to construct a gamma. Gamma S is equal to gamma 0 of 3s. S is between 0 and 1/3. Like you go here in the first 1/3 of the time to reach this point, and equal to B if S is between 1/3 S and 2/3. 1/3. If S is between 1/3 and 2/3, so I will stop at B for those moments, and then I will get gamma 1 over 3 minus 3s if S is between 2/3 and 1. S is between 2/3 and 1. I will go back. So this is a curve. Okay, remember that we have a lot of curves. I have a lot of curves. I'm going to show that this gamma is homotopic to 0. I'm going to show it is homotopic to 0. So how do I show it? I'm going to construct the following lambda, capital lambda. Before I write down the complex formula, I tell you how I do it. You see, gamma 0, I start from 0, reach to b in 1/3 of time. From 1/3 to 2/3, I just stop at b. I don't move. And from 2/3 to 1, I'm back. Okay, this is a gamma. And what happens if I have middle step? For the middle step, if I get, let's assume we have gamma t. Gamma t, I do not reach the b. I reach this point is called capital gamma 1 minus t and t. Capital gamma 1 minus t and t. I reach this point. I just go half, not half, part of my complete trace. Okay, so I stop at 1 minus t. And then this is the first 1/3 of time, as is from 0 to 1/3. If t is equal to 0, you see, this depends on the t. If t is equal to 0, you will go to the top point. If t is not equal to 0, it is increase, then you actually you actually moves less and less. Like for example, here you possibly will just move this place, and here move this place. And when t is equal to 1, you actually do not move. You just get the point A. Right? Okay. So anyway, at t time t, for the trace t, I just move to 1 minus t. That's a first 1/3 of time. And between 1/3 and the 2/3, I'm going to do what? 1 minus t. This is fixed. This t is fixed. I'm going to go this way. Every point, its first coordinate is going to be 1 minus t. I go this way. Go. How do I? Hold on a second. Let me. Okay. So, in the first third of time, I move along. What's that word? It's a longitude. Longitude. From south to north. And between 1/3 and 2/3, I move along latitude. Yeah, from west to east. From west to east. Reach this gamma 1. Reach the gamma 1. And between 2/3 and 1, I work along longitude again, but go back. Okay, so that is the idea. So every t I will go this way. So if you move to here, possibly you go this way, and move to here, you go this way. Okay, so every time you do such movement, that is the idea or the information encoded by the following extremely complex formula. Okay, so it is 3s 1 minus t and t. S is between 0 and 1/3. Okay, you see, its biggest point is 1 minus t. 3s, s equal to 0, it's a. S equal to 1/3, it's just 1 minus t. So you just rescale it to the 1 minus t. And possibly if you move along this point, you will go this way. All right, so that's the first one along the longitude, and then you go with the same along the latitude, So your height your height does not change, so it's always 1 minus t in the first coordinate, and then you move cross from this to gamma 1. So how do we cross it? It's a slightly complex, but well, it's a 3s minus 1 plus 2t minus 3st, and here this t is this 1/3, 2/3 interval. Okay, 1/3, 2/3 interval, and you can check that when you have 1/3, you do have t. You have 1/3, this is 0, this is a t, so it's this point. When you have 2/3, you will get 1. 2/3 you get 1 at this point. All right. And in the final part, we already reached the gamma 1, so we're going to along gamma 1. Gamma 1 is from 1 minus t, but you have to go backward. So it's a 3 minus 3s. If this is gamma, yes, it's from 2/3 to 1. Okay, so that's the idea of this complex formula. If you just check the formula, it looks very complex, but if you check the geometry, it's not that bad. That's how you work it. So this one implies what is a gamma? Let's see. Gamma 0. Let's see. Gamma S0. Gamma S0 is it's 0, right? It's a gamma, not S. T is T is between. This is all about t. T is between 0 and 1. When t is 0, you will have a gamma 3s and 0. No, it's still s. It's still s. My bad. I'm so sorry. Yeah. This is okay, hold on a second. Let me. Oh yeah, I think I should mention that this capital gamma is a capital gamma between the gamma 0 and the gamma 1. Correct. So this is equal to little gamma of 3s. Little gamma 0 of 3s. And when it is between, this is all about s. S belongs to this. S belongs to this interval. S belongs to this interval. When t is 0, it is a gamma 1. T is 0. This is 0, 0. It's a 3s minus 1. So it's a fixed there. It's fixed there. So s belongs to 1/3, 2/3. This is always b. Remember what is, whenever you have a 1, the first one is always b. And the 1 s belong to the 2/3 and the 1. Here t is 0, so it's a gamma 1 over 3 minus 3s. See, gamma 0, 3s, b, gamma 1, 3 minus 3s. So this is exactly little gamma of s. And when you have lambda s1, when t is 1, so you have t is equal to 1, so it's a gamma 1 minus 1, 0, 0, 1. S belong to 0 and 1/3. 0. 0 is always a, so it's a. And 1s is between 1/3 and 2/3. So here t is equal to 1. T is equal to 1. This is still 0. And whatever here, whenever you have 0, it's always equal to a. And the final one, t is equal to 0, it's a gamma 1 over 0. gamma 1 to 0 is still A. So it's a constant A. And this is a continuous function, so gamma is homotopic to 0. All right? So that's the stuff. So if we have fixed point, a fixed endpoint homotopic, if gamma 0 is homotopic to gamma 1, fixed endpoint homotopic, then gamma 0 minus gamma 1 is homotopic to 0. Okay, that's what we actually proved. We'll actually prove this result. With this result in mind, this one is a closed rectifiable curve homotopic to 0. The integral is integral of a constant. Integral of an analytic function along this is equal to 0. So we do have our next important theorem: independence of path theorem. So if gamma 0 and gamma 1 are two rectifiable, not closed, rectifiable curves in G from A to B, and gamma 0 and gamma 1 are fixed endpoint homotopic, then from here we get the integral of f along gamma 0 is equal to the integral of f along gamma 1. So you have to endpoint, you go this way or you go that way, you have the same result. Actually, I mentioned the idea, but here we officially prove it. We officially prove it. Okay, excellent. We stop the video at this point. Thank you.